Intra-operator parallelism. To begin the discussion of intra-operator parallelism, the very first thing we have to do is talk about how our data gets partitioned across disk drives, because we're going to be reading from multiple disk drives in parallel. So how do we partition a table across many disks or many machines? It's really a lot like a coarse-grained indexing scheme. We're going to separate out some data and store it on one computer, and separate out some other data and store it on another computer. Might look a bit like this. On the left-hand side, we do range partitioning. So on some attribute or some key of attributes, we're going to partition things based on ranges of values. Okay, so in this example, A through E are on the first machine, F through J are on the second machine, and so on. And this is going to work well for us for equijoins, for range queries, for group bys, as we're going to see, because we're going to be able to keep things that are the same value together. Now, of course, it's only equijoins, range queries, and group bys on the partitioning key that benefit from this. Hash-based partitioning is similar, but instead of using ranges, we'll use a hash function. So we'll take every value of the key that we're partitioning on, we'll run a hash function and decide which machine to send it to based on the hash of that key. Okay, and so you can see here that the values A through E are scattered across many machines because there's a hash function that hashes those values, right? Same with F through J and so on. Okay, so all values that match are on a single machine, but two values that are close to each other in, say, alphabetical order could be on very different machines. And then finally, another option is to do round-robin assignment of records to machines. So we might have every tuple go to the next machine in a round-robin fashion. And again, that sort of scatters our values across the machines arbitrarily. But one of the good things about it is it spreads load very uniformly. So you can ensure that there's exactly the same number of records on every machine. Now, shared nothing computing is going to particularly benefit from good partitioning because anything that's not on the right computer when we start is going to have to get shipped across the network to get to that right computer. Okay, so if you have a good partitioning up front, then you can start working on the data where it lives rather than having to ship it somewhere else. And we'll see what that looks like next. To begin with, let's talk about parallel scans. If we want to scan a table, and that table's been partitioned across many disks, that is no problem. We're just going to have all those disks have a scan operator over them, and we'll scan all the disks in parallel. And if all we needed to do was generate the output, then we would just concatenate that output and merge it into an output stream on some machine. Sometimes we have a selection over a scan, and if that selection is on the partitioning key, it can sometimes allow us to skip entire computers, or entire sites, if you want to use that term, that have no tuples satisfying that predicate. So range and hash partitioning can both benefit from this partition elimination, where you skip entire sites on a selection. Now, at every partition, it is also possible to build a local index, like a B+ tree, so that when you do a search, you can use the partitioning key to decide which machine to go to, and then you can use an index at that machine to figure out which block to go to on the disk. Okay. Now, do the indexes differ in the different data partitioning schemes? Not really, in the sense that at every node, there's just a B tree. And based on the data partitioning, that B tree will simply have to index different keys. Now, let's think about how lookup by key works if we have data partitioning. So if the data is partitioned by a function of the key, as in range or hash partitioning, then we can do lookup very easily by routing the lookup only to the relevant node and skipping lookups on all the other nodes. However, if the data is not partitioned on a function of the key, we have to broadcast that lookup to all the nodes. Ask every node, do you have this particular key? And then collect responses from each node, either yes, here it is, or no, I don't have it. What about insertion? Well, insertion turns out to be pretty easy. If data is partitioned on a function of the key, we'll route the insert to the relevant node, whether it's a hash partition or a range partition. Otherwise, if it's not partitioned on a function of the key, then we get to insert the data anywhere we like in some sense. So we can route the insert to any node. So for instance, with round robin, we can just route it to whatever node seems least loaded. An exception to that is if we're inserting to a column that's got a unique key. Then we have to make sure we're not inserting a second copy of that key. If the data is partitioned on the function of the key, we just go to the relevant node, it checks to see if that key is already there, and rejects the insert if it already exists. Unfortunately, if we don't have the data partitioned by key, we have to broadcast this lookup, collect responses to see if anybody has this key, and if everybody says that they do not have the key, then we can go insert the key anywhere, actually. But if anyone says they do have the key, then we reject the insert.